All right, hey everybody. Today we're going to tackle that issue of how do we make a confidence interval if we don't know the population standard deviation. So I've already introduced you a little bit to students' t-distribution, and that's the key to being able to do this. So we're going to walk through that today, make sure we have a good understanding of students' t-distribution, t-scores, and calculating confidence intervals. So we still are talking about a sample size of n. The sample mean x bar is still a point estimate for you. But now, instead of knowing the population standard deviation sigma, we don't know that. Okay? Instead, we know the sample standard deviation, and remember, we just use a lowercase s for that. Now, we know that z-scores are calculated by taking x minus the mean and dividing it by the standard deviation. When we do a t-score, we're going to take x bar minus mu, and we're going to divide it by, remember, this is the standard deviation of the x bar, so it's similar to what we've done before. And this is just here for you to know. It's not actually something we're going to be using today, but notice that t-scores are calculated in the same way that z-scores are. Okay? Now, we do have a new term here called degrees of freedom. Okay? And I don't think I'll describe it in this video today. Maybe I'll make a separate video to understand why the words degrees of freedom are used. But our degrees of freedom is always our sample size minus 1, right? So if I have a sample size of 3, the degrees of freedom would be 2. If I have a sample size of 40, the degrees of freedom would be 39, all right? Now, here is a sketch of the different distributions depending on the degrees of freedom, okay? So our student t-distribution has a slightly different shape depending on the degrees of freedom, which depends on the sample size. Notice that they're still symmetrical about the mean 0. Okay? The fewer degrees of freedom, the wider the tails end up being here. Okay? And like I've mentioned already, right? If we're doing like a 90% confidence interval, I know 5% of the data would be in there, okay? And this would be my critical z-score, okay? But now since the tails are wider, let's say I'm looking under this blue distribution, to get that same area of 5%, I'm probably having to slide maybe way out here somewhere to still get that same 5%. So this is 5%, they're both 5%. And we make it wider because if we don't know the population standard deviation, we can be less certain on how good we feel about our interval. And so from here, we get that critical t-score, okay, instead. Okay, so still bell-shaped, thicker curves. As the degrees of freedom increases, it approaches a standard normal distribution. So notice, here's a distribution with 1 degree of freedom. And as the degrees of freedom increase, it approaches that standard normal distribution. All right. Oh, I'm blocking this. By the way, it is a family of curves. So it's not just one curve. There's lots of different curves depending on our degree of freedom. That's what I mean by a family of curves. Okay. Now, when we knew the population standard deviation, we used the critical z-score for certain confidence levels. And we're familiar with the z-score needed for 90%, 95%, 99%. But when this population standard deviation is unknown, we find the critical t-score for our confidence interval. And just like z-scores, we want the area between those critical t-scores to equal our confidence interval. Now, how do we know what those are? Because it depends on what the curve is. So we have a table in the back of the book that I want you to open up to now. It's table 5. Right back here, it says on the top, table 5, t-distribution. Okay? And what I want you to look at is how this table has degrees of freedom on the left side. Okay? And across the top, it says level of confidence, 0.8, that'd be an 80% confidence interval, 0.9, 0.95, 0.98, and 0.99. So those are the confidence levels of percents that we're interested in. You can ignore the 1 and 2 tail part for now. That's going to come later when we do hypothesis testing. And we can see, so how do I read this? Well, if I have 1 degree of freedom, the critical t-score for a 90% confidence interval is 6.314. Okay? Whereas if I want a 99% confident interval for 1 degree of freedom, it's 63.657, right? So a really huge t-score. And that makes sense because our degrees of freedom is only 1, right? It means our sample size is actually 2. That's a very small sample. And what you're going to notice as the degrees of freedom increase, so as we go down in our table, we see those t-scores get smaller and smaller and smaller because the larger the sample size, the closer our t-distribution is going to be to a normal distribution. In fact, when you go all the way down to the bottom, I see 40, 45, 50, 60, 70, 80, 90, 100, 500, 1,000, and then they have an infinity in there. And if the degrees of freedom were infinitely large, you will recognize 1.645, 1.96, 2.576, or 575, I think is what we've used. Those are our critical z-scores for 90, 95, and 99% confidence intervals. All right? So what we do is we say, okay, what's our degrees of freedom? What's our confidence interval? And we find the critical t-score from the table. All right? Now, what happens, okay, so we've got the numbers 1 up to 40, but then it starts to jump around 45, 50, 60, 70, 80, and so on. What if my degrees of freedom is not on this table? What if it's 43? What if I have 43 degrees of freedom? How do I do that? Well, our rule is you're always going to round down. Okay? Even though 43 is closer to 45, we're going to round down to 40. Because if we were to round up in degrees of freedom, that would make us more confident than what we actually are. Okay, it would narrow our interval by producing a smaller t-score, and we're not that good. Okay, so we don't want to be kind of like overconfident. We always want to say, you know what, this is where I'm at. I can't say that my degrees of freedom are higher, but I can always go lower and just widen out my interval and feel okay about that. So our rule is to always round down on degrees of freedom if it's not in the table. Now, I hope you're asking after our last activity, I'm jumping ahead of myself a little bit. So when we're construct a confidence interval, again, we have error, and this is going to be calculated the same way that we calculated error when we were working with z-scores. But instead of a critical z-score, it's a critical t-score. And instead of sigma divided by the square root of n, it's the sample standard deviation divided by the square root of n. So same formula, but we're switching the z-scores out for t-scores and sigma for s. Okay? Population standard deviation for sample standard deviation. We can still construct our confidence interval by taking our x-bar, subtracting the error, and adding the error to set up the bounds of it. All right, now what I was going to get ahead to here a little bit is based on our last activity. You should probably be asking, what's the criteria? Okay? The criteria for creating a confidence interval using t-scores, okay, is the same as the criteria for using z-scores. Okay? The sample still needs to be random, and the population must be normally distributed, or the sample size must be at least 30. Okay? So we have to meet that criteria to be able to perform a confidence interval with a population standard deviation that is unknown, where we only know the sample standard deviation. All right, let's get to one of two problems that we're going to be looking at today. Okay, I've got my table ready here for when I need it, but let's look at our problem. Suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Okay, that's exciting, right? They're doing these digs and they start to find these fossils of some type of miniature horse that they didn't ever know about, right? And reconstructions of the skeletons show that the shoulder heights of the horses are below. So that would be one thing that scientists might be interested. How big were these miniature horses? Okay. Have you ever wondered when we get type of information about dinosaurs or whatever, like how do they really know how big they were? Okay, it's not like we could look at all the dinosaurs of that type. It's not like we have all the miniature horses from that species to find the average height. Okay, but what we do have is we have the height, okay, to the shoulder of 1, 2, 3, 4, 5, 6, 7 different miniature horses here. Find a 99% confidence interval for the mean shoulder height of the entire population of horses, right? There's no way that we could possibly know the standard deviation of the population. So we're only going to work off the standard deviation of the sample. Okay. Now, hopefully you're saying, stop. Did we meet the criteria? Okay. Is the sample random? There might be some bias depending on what happened here, but I would say overall, if we're finding fossils, that it's probably going to be fairly random. I'm okay with that. Is the population normally distributed or the sample size at least 30? Well, our sample size is only 7, so we need the population to be normally distributed. And we don't have that information here. So if you got this problem, okay, I would expect you to say, Mr. Mayor, I don't think that we can perform a confidence interval calculation because we don't know the population standard deviation. The population is normally distributed and we don't have a sample size of 30. All right, so we want to make sure that we're checking that. Okay? Now I will tell you this, and I want you to consider this: heights, shoulder heights, heights of people, length of feet, those type of things, aren't they usually normally distributed, right? Where you have most around one height, you end up with some that are a little taller, some that are a little shorter, but it tends to be normally distributed. So I'm going to make that argument here, and even though it wasn't in there, we're going to do this problem so we can learn how to do it. All right? So what do we need to know? Well, we need to know the sample mean and the sample standard deviation. So I'm going to grab my calculator, and I am going to go into Stat Edit, and I'm going to put these samples into list 1. So 45.3, 47.1, 44.2, 46.8, 46.5, 45.5, 47.6. All right, I've got all 7. Now I'm going to go Stat, Calculate, one variable statistic. Mine's in list 1. Do not have a frequency list for this one, so I'm going to clear that out. I'm going to choose Calculate, and I get X bar to be 46.14. Well, we'll go nearest tenth since these are all nearest tenth, 46.1. And our sample standard deviation, remember that's the one with the S and not the sigma. So it's the S with the X after it. It's 1.19. Yeah, we'll go 1.2 nearest tenth again. All right. So we've got that. What else do we need? Well, to calculate our error, we need our t-score and n. And to get to our t-score, we need to know n, which is 7, and we need to know our degrees of freedom. And if our sample size is 7, our degrees of freedom is 6. Now we're doing a 99% confidence interval. Okay. So we need to look up a t-score for 99%. So this is where we go to the book. I'm going to go to a level of confidence of 0.99. I'm going to go down on my table until I hit 6 degrees of freedom, and then I'm going to go over. So I'm seeing 3.707. Okay. So that's how we look up our score. Instead of just using 1.645, 1.96, 2.575, we have to look it up in the table each time. It depends on the degrees of freedom. All right, so we have that. Now we're ready to calculate our error. And recall our error is our critical t-score times our sample standard deviation over the square root of n. So for us, this is 3.07 times 1.2 over the square root of 7. So we get an error of about 1.4. Okay. So then what we do, we take our X bar, which is our point estimate for mu, we subtract 1.4, and we add 1.4. So 46.1 minus 1.4, 44.7. Now let's add 47.5. So I'll type this out instead of writing. We can say we are 99% confident that the actual mean shoulder height of this species of miniature horse is between 44.7, these are centimeters, and 47.5 centimeters. And that's a pretty cool thing to be able to say. All right, let's look at one more. The number of wolf pups in wolf dens of the southwestern U.S. is recorded below for 16 different wolf dens. Okay, so they went into wolf dens, they counted how many pups there were. Assuming the population is approximately normally distributed, give a 90% confidence level for the mean number of pups in wolf dens in the southwestern U.S. Okay, doesn't say it here, but I would assume that this would be random wolf dens. It is normally distributed population for the number of wolf pups in a den. So we're good to move forward. So just like in the last problem, we need to know what our sample mean and our sample standard deviation is. So I'm going to grab my calculator again. Stat edit. Let's clear out the list from the last problem. Here we go. 5, 8, 7. Okay, good. And I always double check that, okay, I did put in 16 numbers and there were 16 numbers there. So that's good. So let's quit out of that. Stat, calculate one variable statistics. And our mean, 5.625 wolf pups per den. Sample standard deviation, 1.784. All right, what was our sample size here? 16. That means our degrees of freedom are 15. We look up the critical t-score for a 90% confidence interval. That's 0.90. So we go to our table. We find 0.90 on the top. Level of confidence. We're going down to 15 degrees of freedom. 1.753. Excellent. Let's calculate our error. T-score times standard deviation over the square root of n. Okay, I get about 0.782. So we can take our sample mean and subtract that, and then add it. See what we get. Oops, I added first. 6.407 and 4.843. So interpreting it in the context of the problem, we are 90% confident that the true mean number of pups, wolf pups, in dens in southwest U.S. is between 4.843 and 6.407 pups. There we go. So I hope you don't think that's too bad. I don't either, but it's a really cool step, and it was a step that was really needed. I'll wrap up our video now. Thanks for watching. We'll see you next time.